Alright then, okay, so we're going to move on to Archimedes Principle. Now in the first video we got this equation right here, that pressure equals the height underneath the water times by the density times by gravity, and that gives you the pressure that you would experience at that depth in that liquid. So what we have here is a situation where we've got something that's underneath the water. Now, we agree quite heftily that there is forces coming from everywhere on this. Pressure must be coming from everywhere to squish this block. So we've got a force downwards, you've got a force upwards, you have forces sideways as well, keeping it in position. So we're not interested in the one sideways, but we are interested in the one that keeps things afloat, and that is called upthrust. And the aim of today's derivation is to get to an equation that represents upthrust. And we're going to start with where we ended up in the previous video. So what we have here is we have the force down. Now in the previous video we worked out that the pressure downwards was equal to h rho g. The force then acting downwards would be equal to h rho g a, because, I will tell you why, because pressure equals force over area, therefore force equals pressure times area. That's the pressure, there's the area. So just bear that in mind in this case. So we've got a force downwards of h rho g a. And we've got a force, what would potentially be as a result of the pressure of the depth. So I'm just going to rub out the word upthrust. We're going to start with the pressure. So pressure is equal to h rho g at that depth. Now, bear in mind, this surface here has some extra depth. It's got extra depth. So that means there's an extra amount of depth here, and we're going to assign that a letter, the same letter it's assigned in your book, which is x. So this pressure becomes slightly different. It's h plus x rho g. Okay, so you've got h plus x rho g. And so what we end up with here is when we transfer this into a force equation, as we did before, we get force is equal to h plus x rho g a. So let's have a look at what we can analyse here. We've got a force downwards of this, and we've got a force upwards of this. Now, interestingly enough, what happens if we essentially resultant out these forces? What's our resultant? Well, essentially this is going to be the bigger value, but we can expand this out. We can make it a bit more easier to read. So it becomes force is equal to h rho g a plus x rho g a. Okay, because I've just done the timesing and I've opened it out. So that means the resultant force would be minus that final value. I'm just going to move this out because otherwise it's going to get very busy. So minus this value here, h rho g a. Just write that back in. So, what can we do with this to simplify it? Well, I've got that is exactly the same as that. So therefore, they cancel. And that leaves us with a remaining force that acts upwards on this object, which is, and I'll write this up here, force is equal to x rho g a. Now that is pretty much there. Now you might be thinking, well, we need to go through that equation just to make sure we're happy with what that represents. So this, in equation form, is Archimedes' principle. But we can simplify it even further. X and A. Well, X is that side of the object. A is the surface area of the object. So, if you were to times those two values together, yeah, well done if you guessed it, that's the volume of the object. So let's rub this out. Rub out A, V rho G. Now be careful. The volume here is the volume of the object itself. The density, this is where a lot of people come unstuck. The density is not, I repeat, is not the density of the object. It's the density of the liquid that it's in. So in this case, it's the density of water. And G is, as we would expect, is the gravitational constant, which is force due to gravity. Acceleration due to gravity, sorry. So this force is the upthrust that the object under a liquid will feel. And that force is directly proportional to the volume of water displaced. And there we are at Archimedes' principle. The force is directly proportional to the volume of the liquid that's been displaced, in this case, water. So we've got an upwards force that is equal to the volume of the object times by the density of the liquid that it's in times by G. And so we have our final Archimedes equation. Now, I'm not going to do an example in this video, we'll do it in the next one, but the next few videos will feature some examples of how to use this equation and where we can become a little bit unstuck with it if we are thrown a loophole. Okay, so have a look, have a read. Both the derivations I've done so far are in your textbook, okay? They're not explained like I've explained them there, but I've shown you all the algebra and the steps. Do watch this video again if you need to make sure you're happy with it, because it's nice to see where these equations come from, and you need to get to be able to use them in any questions that might come your way.